Okay, Cappuccino, you have the option of listening to me or just looking at the example on page 124, example 14, and reading the example. But if you are choosing to do reading the example, I do want you to know that they have a wrong answer in here. So on letter D, T equals 1.6, not 0.6. Okay. Another thing, if you weren't in class, I'm going to point this out in class, but if you are in the electronic copy of the textbook, these are links. This one is a link to calculator instructions because you are actually going to use your graphing display calculator on this problem. And this is a video of another teacher walking you through this example. So go ahead and check those out as well. So here's me doing the problem. So hopefully you have your book open to page 124 or you've looked at it, because I can't have this showing and my work at the same time. So I am going to have the book next to me while I talk through this problem. Okay, so here's the information they give us. We have a model boat that is called A, and it's starting at 2,5 at time 0, and it's traveling at a speed of 4 meters per second in the direction of the vector 3, -4. And then it says the x component is east. So east is that way. That's our x direction. And the north component, the y component is north. This would be north. All right, so that looks pretty traditional. So it's set up in a normal coordinate grid. Nice for us. Okay, so it says the first question is find an expression for the position vector of A, and then in parentheses, vector r sub a at time t. So a position vector, when we think of a position vector, like A right here, its position vector would be 2, 5. Okay, but this boat is not going to stay there. So it's only there at time 0. It's going to be moving. So if I want the position of this boat, I'm actually going to have to write the equation of a line because it's going to be moving. So that's why they give us this r sub a. So r sub a, we're going to write the vector equation of a line because it's going to be moving. So we know it's starting at 2,5. That's its starting point. So that's our position vector for its start. And then we need to find its velocity vector times t. So we know its speed and we know its direction, and we've been practicing how to make velocity vectors. So let's go ahead and do that. So our velocity vector, do it over here on the side. As we were practicing in class, you take the speed, in this case 4, divide it by the magnitude of the direction. So that would be 3 squared, square root of 3 squared plus -4 squared. And that's going to be a scalar. That's just going to be a single number. And then you're going to multiply it by your direction vector to get the velocity vector. Okay, so if I simplify this, notice this is 3, 4, that's going to be equal to 5, right? This is a 3, 4, 5 triangle. You can go ahead and put it in your calculator and make sure. So I have 4 divided by 5. 4 divided by 5 is 0.8. So I'm going to have 0.8 times 3, -4. So my velocity vector is going to be equal to, I already did it on my calculator, so I'm going to just write it down. My velocity vector is going to be 2.4 and -3.2. That's my velocity vector after I multiply both the 3 and the -4 by 0.8. There's my velocity. Okay, so I'm going to go ahead and write my, what do they call it again? My position vector for boat A. I'm going to write it now, complete. My position of boat A can be found by taking its initial position and adding to it the change, which is 2.4 and -3.2 meters per second times time. And that'll give me wherever the boat may end up. All right, so I want to just talk about this again. Remember, this is where the boat started. So it's its starting point. This is the motion, okay? This is its speed. This is how fast it's moving. This is how it's moving. And we multiply that by time. So, right, like we do speed times time to get distance, okay? And this is where it ends up. So this is where it is. So this is position of the boat. hence our calling it a position vector. So this position vector, it's not just in one position. Since it's moving, we have to have a variable in there, which can help us calculate exactly where it is at any given time. All right, let's go ahead and graph it too. What would this look like if we graphed it? So I'm going to graph this line. So just like we practiced when we first learned what the vector equation of the line is, we start by plotting its starting point. So 2, 5, it's right there. And then I can use this 2.4 over and negative 3.2 down. That's going to be, let's see, 2.4 over and 1, 2, 3.2 down. Yeah, it's probably going to be about like that. Or what would be even easier is to actually use this vector to help me get my slope, because they have the same slope. This is the same slope as this, because remember, all we did was we took 3, negative 4 and multiplied it by a scalar, so it's still the same slope. So 1, 2, 3, 1, 2, 3, 4. Oh, look at that. They're all lined up. Okay, so I can now graph from my starting point. My boat is going this way. So who knows where it's going to end up, but this is where it starts and it's going down that way. So there's my boat A. So here's boat A starting there and it's moving that way. Okay. One thing about the velocity vector, just to make sure you understand, we said it was moving 4 meters per second. So this means it's moving 2.4 meters per second in the X direction, and it's moving negative 3.2 meters per second in the Y direction, which gives us a speed of 4 meters per second. Okay. So if we took the magnitude of this vector right here, if we did 2.4 squared plus negative 3.2 squared, added them together and took the square root, we would get 4. Its magnitude is 4. Okay, so there it is. We graphed that. All right, you didn't have to graph that. That's not part of the assignment, but I just like doing it just to explain. Okay, part B, they give us more information. So the next information, a boat B has position vector given by R sub B is equal to 3, negative 2. So remember, that's its starting position. Plus, and they give us its velocity vector, 2, 1, t. So they did all the work for us on boat B. Okay, they might have given us information like this again and made us do it, but this time they just gave it to us. So that's cool. So let's go ahead and graph boat B. So it's starting at 3, negative 2. Here's boat B. It's going to start here, and then it's going to move in this direction. Every second, it's going to move 2 meters to the right and 1 to the east and 1 meter north. Okay, and I can keep doing that. So it kind of looks like these boats are going to smash into each other. But are they? Are these boats going to smash into each other? It looks like they're going to smash into each other right here. And that's the subject of the next question. It says, show that the two boats do not collide. They don't collide. Why not? It looks like they're going to cross each other. So it says, though, show that they're not going to collide. So why is it possible that they're not going to collide? It's because they are both moving. So if, say, boat A is moving really slow and boat B is moving really fast, boat B will be long gone by the time boat A gets here. Okay? So it's quite possible their paths are going to cross, but that does not mean that the boats are going to run into each other, because boat A might get to there after boat B has already passed. Okay, so let's see, how can we show that they're not going to collide? So if we wanted to find the intersection of two lines, what would we do? We would set them equal to each other. So that's what we're going to do. We're going to set them equal to each other, and then we're going to try and solve for t, solve for the time that they're going to crash into each other, and you're going to see what's going to happen. Okay, so I'm going to take boat A, so 2, 5 plus 2.4 and negative 3.2 t, and set it equal to boat B. Okay, now that's a giant mess, right? So we can actually simplify this. Remember how we can write things in parametric form? We can write this as just one giant vector. We can do this. The x component is 2 plus 2.4t, and the y component is 5 plus negative 3.2t. And we can rewrite this one also the same way. So we have 3 plus 2t and negative 2 plus t. And then to simplify things even more, I can separate it to the x components. So I'm going to write the x components. 2 plus 2.4t is equal to 3 plus 2t. And the y components, I'll do that one down here. 5 minus 3.2t, I hope you're okay if I change plus and negative to just a minus, is equal to negative 2 plus t. All right, so now we're going to solve both of these equations, and you're going to notice something weird happens. So let's solve this. Minus 2 from both sides, I get 1. Minus 2t from both sides, I get 0.4 is equal to 1. Divide both sides by 0.4, and I get 2.5. Okay, so at time 2.5, their x coordinates are going to be the same. And then if I do this one, add 2 to both sides, I get 7. Add 3.2t to both sides, I get 4.2t. Divide both sides by 4.2, and I get 1.67. What the heck? What does that mean? So here at 2.5 seconds, it's telling me that both boats are going to have the same x component. So they're going to have the same x component. I'm going to make a little sketch of that. So at 2.5 seconds, boat A and boat B are both going to have the same x component. So their x's are going to be the same. So that means like this. So like here's boat A and here's boat B. They are going to be north. One is going to be north of the other one. One's going to be south of the other. They're going to be lined up like this at 2.5 seconds. And then here, the y components, okay? These are the y components. This is the y, this was the x. So at 1.67 seconds, they're going to have the same y component. So when they have the same y component, so it's going to be like this. One of them is going to be, they're going to be east and west of each other, okay? One of them is going to be east of the other, okay? So when the x components are the same, they're going to be lined up north-south, and if the y components are the same, they're going to be lined up east-west. But notice the times are different. So we don't have both the same x and the same y at the same time. That's why they don't collide with each other. They are not going to collide, okay? Because it's happening at two different times. They're not at the same x value and the same y value at the same time. Okay, moving on. Part C. Do I have a plain piece of paper under here, I hope? Because I'm running out of room on here. Part C. It wants to know the shortest distance between the two boats. And when does that happen? At what time t does that happen? Okay, so here's my boats. So notice they start far apart and they're moving. And one is moving at 4 meters per second. This one is moving slower. Okay, you can tell just by looking at the slopes. This one's moving slower than that one. So this one is moving square root of 5 meters per second, right? If we took the magnitude of that, 1 squared plus 2 squared, and took the square root of those added together, square root of 5. So this one's traveling at a slower speed. Okay, so if we look at this, they are going to be getting closer and closer, and they're going to pass each other, but we don't know exactly when are they going to be at their closest. Okay, so how are we going to get them at their closest? Well, I want to write an expression for the distance between A and B. So think about our warm-up. If I had my position vector A and my position vector B, and then I wanted to know the distance in between them, so my vector AB, I want to know that. I want to know the distance here. I want to know the magnitude of that vector. I need to find my vector AB, okay? So I want to know what is my vector AB. So remember how we do that. We do B minus A. But B isn't just a set of coordinates. What is B? B is this whole equation. And A is not just a set of coordinates, rather it's this whole equation. So we're going to subtract these two equations from each other. Okay, so notice how like here we set them equal to each other. Now I'm going to be subtracting them. So the easier way to do this is to have them rewritten like this. Okay, so we took, which one was this? This was boat A, and this one was boat B. We're going to use these again. okay, how we put them together. This was my boat A. This was my boat B. But now we're going to subtract them. So here's boat B. So the coordinates for boat B, we don't know exactly where it is, right? Because it depends on time t, but we can use this to represent B. So B is going to be 3 plus 2t, negative 2 plus t. And we're going to subtract the coordinates of A. The coordinates of A is right here. Because again, we don't know exactly where it is yet because we don't know what t is. Okay, so there's the coordinates point A. Now if we subtract them, let's go ahead and simplify this. We get 3 minus 2 is 1. And then 2 minus 2.4 is going to be negative 0.4 t. And then down here, negative 2 minus 5 is negative 7. And 1 minus negative 3.2, well, minus a negative, watch out, becomes a positive. So 1 plus 3.2 becomes 4.2. T. Okay, so this is my vector AB. Now I want the magnitude of that. I want the magnitude. That's how we get distance. I want the distance of this. So I'm going to do square root of the x component squared plus the y component squared. Okay, now what? I want to know when this is small. How small? I don't know. As small as it can get. I know it's not going to be 0 because the boats never collide. So the distance between them is never going to be 0. But how close do they get? How close do they get to colliding? What's the closest they get to each other? So in order to do that, this is where we're going to use our graphing display calculator. Okay? Because I want to minimize this. I want to find its minimum value. So we could use calculus. We could find the derivative and figure out when the derivative is equal to 0 to get the minimum value. But who wants to do that? I don't know. Maybe one of you or two of you do, but I don't. Okay, so this is our distance. The distance between the two boats is, we get it by doing this function. So I'm going to put this function into my graphing calculator. Oh, and what do you know? I already have it in there. Because this is the second time I made this video. I messed up the first time. All right, so I already put it in there in my y equals. And then I'm going to graph it. And you might need to play around with your window. I did a zoom 0 so that I could see it better. Okay, so you might need to play around with your window to see it. And I want to know when is the distance at a minimum. Okay, our x value is time and our y value is distance. So I want to know my minimum y. So you can see the minimum is right here at the bottom here. And we can have the calculator find it for us. So we're going to say, oops, we're going to say second calculate and choose minimum. And we're going to go to the left of it. And we're going to go to the right of it and ask it to guess. And it gives me, you probably can't see it because it's really tiny and out of focus, but it tells me that the coordinates of that minimum point are 1.67 and 0.332. So I'm going to go ahead. When we use the GDC to prove that we used it, I want you to make a sketch. Okay, show me what you saw on your calculator. And it can just be a sketch. Okay, so we got a sketch. Yeah, my sketch is really bad. Okay, so that minimum, the minimum value is 1.67 and 0.332. Okay, so what does that mean? What does that mean? So remember, our x value was the t. This is our t, and our y value is the d, the distance. So at 1.67 seconds, the boats are about 1/3 of a meter apart. The boats are 0.332 meters apart. Okay, this time looks kind of familiar to me. 1.67. What else happened at 1.67? We seem to have seen that someplace else, haven't we? Okay, so anyway, I'll let you think about that for a minute as we go on to question D. Question D says, find the value of t at which B is due east of A. So I want B to be east of A. I want it to be east of A. Now, does this look familiar? I want to know when B is east of A. What do we notice about the coordinates of these? Notice this has some value x and some value y. And B has some value for x and some value for y. It's when the y values are the same. When the y values are the same, these boats will be due east of each other. Well, one of them will be east of the other one. So I want to know when their y values are the same. Okay, so we have their y values right here, and right here. So y value, -2 plus t, when is that going to be equal to 5 minus 3.2t? So if we solve this, I'm going to add 2 to both sides, equals 7. Does this seem familiar? Haven't we done this before? Add 3.2 to both sides, I get 4.2t. Divide both sides by 4.2, sorry. So 7 divided by 4.2, 7 divided by 4.2 is equal to 1.67, or 1.6 repeating, 1.67. Hey, that's when they're at their closest. They happen to be due east of each other at the same time that they are close together at that 1/3 of a meter apart. So if we go back and look at our graph, well, where's 1.67 seconds? Okay, our graph, where's my graph? Our graph doesn't have time on it. Remember, this just has X and Y. It doesn't have time. So if we want to find out where are they, I would actually have to plug this back in to my equation. So where is point B? Point B, when t is equal to 1.67, I can plug in 1.67 here. So B is going to be 3 plus 2 times 1.67. By the way, this is like extra information I'm giving you now. They don't have this in the book. I'm just trying to give you a little bit more explanation. And point A, where is point A going to be? Point A is going to be at 2 plus 2.4 times 1.67. And 5 minus 3.2 times 1.67. Okay, so if we multiply these out, 3 plus 2 times 1.67, 6.34. And then -2 plus 1.67 is -0.33. And that's where boat B is going to be. And boat A, where is it going to be? 2 plus 2.4 times 1.67. And that's 6.01. And then the last one, 5 minus 3.2 times 1.67 is -0.344. And did I miss a? No, I didn't. Okay, so if I were to graph that, if I were to graph these points, this is at the same time. This is at the same time. These are where the two different boats are, and this is the closest they get to each other. They're going to be 1/3 of a meter apart, about 1/3 of a meter apart at 1.6 seconds, and this is where they're going to be. So if I look at my graph, 6.34, 1, 2, 3, 4, 5, 6.34, and -1/3. Oh, right there. There's my boat B. And then for boat A, it's going to be at 6.1. 1, 2, 3, 4, 5, 6. That's 6.1. It's 0.01. Sorry. That's like basically 6. And -3.4. Aha. Right there. See? That's where they are at 1.67 seconds. They happen to also be due east of each other. Look at that. They're due east of each other, and that's as close as they get to each other. Because remember, B is heading this way, and A is heading this way. So that's as close as they get, is right there. Bam. Okay? So lots of good stuff in this problem that's going to help you do some problems on your own. So good luck with that. And time to stop recording.